Okay, so I sent a mail just now that the final exam apparently finally has been fixed. It's on December 7th. Isn't that the World Harbor Day?
Yes.
Yeah, so it's a very fitting exam day. so Arizona would be sun. So that's on Wall 7 at 12:10 to 2 p.m. And of course, Steve Hawking, who actually was talking about this, basically said there's a huge value in getting it right for the exam because apparently AI otherwise is going to kill everybody. I don't know if you're reading all this stuff. Steve Hawking is really worried about what you guys are going to do with AI. But I think he had an Reddit AMA, right? Where he was talking about all sorts of things. Including, I think he said, the most mysterious thing in the universe is women. I don't know. It's like, I guess, it's in his element for whatever reason. Anyway, we did the class feedback thing. I actually have to go through it all, but these are the easy ones, the ones that the system itself shows. Of course, things are all over the place. And also there's a large number of comments on written comments. As I said, I looked at some of them, not all. I haven't really digested them. But it did look like different people had different problems in terms of too long a homework or too hard a project, or even some people thought my accent is a problem. And I thought I was actually preparing you for jobs in Silicon Valley because this is what you'll hear if you go to Silicon Valley. Okay, I mean, I can speak in the Midwestern accent, but I think it will be helpful for you if I do my Indian accent. But anyway, so I was, being in a malleable mode, I was going to just sort of get rid of the homeworks, make the projects easy, make the exams really small and so on. And then I did see one comment that a student wrote, and I said, maybe not. So apparently you're all a bunch of babies. So. More seriously, I guess, as I said, a couple of things I will try to do. I think people wanted more small videos with just the technique rather than, I guess the class would be used for the overall background. And I think we go over the techniques, but I think people like alpha beta pruning short video or the A-star search short video. So I'll make a few of those, hopefully, and then make them available for each of the topics. So that I would try to do, and then I think people wanted the first half to be smaller so that they don't lose focus. We will deal with that. We'll probably today, I'll remember to, if I don't remember, just remind me, we'll try to start the first half before 2:45 so that, we'll have like a break and then we come back to the second. I'm not really sure what these are all available. I will take a look at this more seriously anyway. Let's see what is. So the one thing, of course, is lots of people basically felt homeworks take a lot of time. It was meant to, take a lot of time because that's how you learn. I mean, if you want the homeworks problems to be put on the exam instead, I will do that. And I think exams would basically be actually somewhat easier if you do the homeworks. I understand that they are very time consuming, but I don't quite know how to learn anything without you spending a lot of time. So that's one thing. Let's see, what else did we actually want to talk about? Yeah, so recitation sessions, I think not most of the people are unable to actually attend. That we know that beforehand. Yeah, so I think that the most interesting thing is the people are enjoying projects. There's always somebody who doesn't enjoy everything, but it's not so much that there's somebody who didn't enjoy any other class, but there are people who didn't enjoy projects but rather enjoyed the exams or lectures or whatever. But by and large, I thought the projects, people are having fun, and I think that's good. So we are anyway, as I said, we're continuing this project. We know that Game Tree Search is the next project. And I put, I think, 2-week deadline on that. I think that, again, I'm making a reasonable educated guess. Actually, these were all 1-week projects, apparently, when the MOOC was done. So the great thing about the MOOC is the completion rate is 1.5%. And, there are like 1 billion people, but, about 1.5 people complete per 100 people. Apparently, you all want to complete this course for whatever reason. So I think we'll have to deal. What I would like to do is, look, I can make a project which has the whole entire semester, but you're not going to learn much. Okay. So I am going to make it 2 weeks, basically. But on the other hand, if with best efforts, if you're like way behind, then we will revisit it. That's the way I would try to do this. But please don't game the system. Just don't do anything, because there'll always be somebody who will do it, and then you'll get sunk. So make sure that and I think it should be easier because you now are familiar with the code base. The third project is actually going to be also on the same code base, which will be on MDPs. In fact, they call it reinforcement learning, but we are not yet doing reinforcement learning. So when you do it, you will just do the MDP part, mark prediction process. So that's where it's going. Okay. What else do I see here? A large number of written comments. Obviously, I'm not showing these here. I have to look at it myself. Okay, so the other thing is that people are actually watching videos before coming to the class. So in fact, some of them felt that me repeating it is not good, so I'm not going to repeat it. And then those of you who are hoping that I will repeat it, I guess you are in for a bad luck. But so that's the way it's going to be. Okay, I will probably say a few more things about this in a mail to the Piazza. But thanks for taking part in it, and this is a good way for me to figure out what's going on. Yes?
I didn't see the slides for the video.
What?
I watched the video, but I didn't see the slides for that one.
It's basically okay. Actually, the problem, that's a good point. So the idea basically has been that, I'll say it again, although I should have mentioned it that time. In general, I'm basically getting the videos that I'm asking you to. Okay, so that's where I'm getting the videos from. I just give you the link. Okay, so for example, the one that you watched was, I believe, 7.1. Okay, so the slides that were used that year were right there. So it is indeed, I think somebody actually pointed out it's hard to read the slides. And first of all, I did not expect you to be reading the slides. I think in the beginning of the semester I pointed out this is where they're coming from. I was just giving the link directly for the videos. If I give these slides there too, they will clash with the slides I'm using this semester, which may be slightly different. So I'm just hoping that you'll remember that you can always go back to CSE 471, and then the slides that were used that time, for this part would be available right there. Okay, that's a good point. Okay. Okay, fine. So what I'm going to do today actually is two parts. In the first half an hour or so, I want to complete a few issues that I left hanging on the planning graphs. And then I will get into propositional logic, continuing from where you left off after seeing the videos. Okay, so that's what I'm going to do. Basically, we talked about this whole planning graph as a structure to get approximate reachability, approximate projection, information. So this is like what actually is done. These are the steps. You can look at them more carefully. And I think the textbook also describes them. But here is one more example. We did one example last class, right? We did this example of eat cake and bake, eat cake and have cake example. So again, I think the planning graph, the data structure, if you draw them for any one of the, for any reasonably sized domain, they become quite long. Okay, so in fact, to some extent, the great contribution of eat cake and have cake example is it is the smallest planning problem for which the graph will fit in the width of a 8.5 by 11 page, and still will make all the points about the mutexes and about the levels at which things come into the planning graph and so on. So I will show you one more example, and then we will talk a little more about how the heuristics are extracted. We did talk about them last time, but I want to do it a little more slowly because in particular also bring up this idea called relaxed plan heuristic. So this was the example that we looked at in the beginning of the planning, right? So if you were to take this example and you have this initial state and the goal is of course not clear B and hand empty. First of all, how many of you think that planning graph requires both the initial state and the goal state? Notice that the planning graph, the way the planning graph is expanded, it just starts from the initial state. Okay. For one initial state, you construct a planning graph. That's basically telling you approximately starting from that state, how many steps do you need to go before certain propositions become possibly true. Right? That's what it is. So goal state is actually the goal for your problem. Planning graph itself doesn't particularly care. Essentially, in the constructing of the planning graph, you don't actually care about it. You will talk about the goal state in the relaxed plan in a little while. For this particular problem, if you basically remember that the actions are pick up, put down, stack, unstack, and then of course, you can put each variables can be instantiated with the block's name, and that would be an actual action. Okay, and so if you were to look at the planning graph for this, it's already pretty much more complicated looking than the simple one that we looked at. Okay, so for example, I'm just writing this is the initial state on table A, on table B, clear A, clear B. Remember that was clear A, clear B, hand empty. In fact, I should have written hand empty. Yeah, there is hand empty. Okay, so this is the initial state, right? And then if you remember the way we talked about planning graph is the first thing before you do anything else, you can do a no-op and just get the same proposition in the next level. Right? So basically, if something was true in level k, it will always be true in level k plus 1. Okay? And so that's sort of the monotonicity of the planning graph. That also ensures that eventually planning graph won't change from one level to another level. Because there are only so many conditions in a finite domain. And if basically they would all have come in at some point of time, or anything that you are actually able to reach with an action would have come in at some point of time, and then there is no more that will change when you go from one level to other level. Okay, that's what is called the level of the planning graph. Okay, so in this particular case, you actually did this here, so you got hand empty, clear B, clear A on table B, and then now I also consider all the actions that can be done in the current level. Okay, again, right now I'm not doing the mutual exclusions, even though at the end of the class, last time I talked a little about mutual exclusions, I'll talk again today. But right now, let's assume there is no mutual exclusions being tracked. So you put up pickup A is basically you put them, links from it to its preconditions, and the preconditions must be present in the previous level. If not, you can't put that action. And then if its preconditions are present, its effects are just written. Now, if that effect is already present in the current level, you just put a link to it. Otherwise, you just write on the effect. Okay. So similarly, pick up B, and also in the way we are doing this, we actually keep track of both the basically the proposition lists are literal lists actually. A literal, by the time now that you actually know propositional logic, you know the point of what the definition of what a literal is. Literal is a proposition or its negation. Okay. So I basically have not hand empty, not clear B, not clear A, hand empty, hand I mean, holding A and holding B. HA and HB are just shortenings for holding A and holding B. Okay. Now notice, this is just the second level. Already it looks slightly complicated, right? Now you do the next level. To do the next level, you realize it's going to be really busy, right? Because all of these will also be present in the next level. Plus, now the one question is, why did we not do things like stack AB action? In this level, why did we put a stack AB action? Because its preconditions are not present in the previous level. It's just mechanical. There is no creativity here. You know, you look at it, take an action, you see if its preconditions are present in the previous level. If so, you put the action in and you write down the effects in the next level. That's what you do. Okay. So basically, next level, that's how it looks. Okay, I think I actually missed a few things, but you know, that's how busy it looks by the next level. Okay, so because it has everything here would also be present there. Okay, and furthermore, there are, and you basically notice that I have actually missed some of the edges. For example, from this on table B to this on table B, there should be a no-op action connecting it. If I do that too, it will be even more busy. You see what I'm saying? But in a data structure, it's very easy to keep track of. Okay, so everything here will also be here. Plus, these are all the actions that can be done now because their preconditions are holding in the previous level. So you are acting as if this list of propositions, which is not an actual single state, you are acting as if it's a single state. Okay, what that means is just because you thought an action can be done at this level doesn't necessarily mean it can be done at this level. But if you thought this action cannot be done at this level, it's for sure it cannot be done. You see what I'm saying? Even with optimistic assumptions, if the action cannot be done, then clearly in real life it cannot be done. In the real planning problem, it cannot be done. Okay, so that's the basic idea of the planning graph. When something is present at a particular level, it only means that it is possible to achieve it with a plan of length that much. It's possible. If it's not present, we know for sure it cannot be achieved by that length. Okay, so possible to, and so the actual number of steps required to achieve something, if it's present in level I, would be at least size I plan or more, which is exactly the definition of admissible heuristics. Because if you think of cost as the number of actions, okay, then admissibility says don't ever consider the cost to be longer than what it really would be. Okay, for any single literal, it turns out this works quite well. Any single literal, if I have a planning graph like this, if I ask you what is the cost of achieving on table A? Okay, so you start from here and look for the first proposition layer where on table A is present. And it turns out on table A is present in the very first level. You're done. So it's 0, cost is 0. If you do anything more than 0, it will be inadmissible. Okay, and similarly, what's the cost of achieving not hand empty? Not hand empty is not present here, but it's present here. Right? Because in fact, hand empty is present here, not hand empty is not present here. Okay, so this is fine. So not hand empty, you need at least a plan of length 1. So the heuristic value is 1. Okay, and so in the A star search, you will basically throw in this 1 as the value. Okay, and finally, let's say something like something. Okay, what's the cost of on AB? So on AB is not present here. On AB is not present here. On AB is present here for the first time. So it's at least 2. Right? So this is the idea of level heuristics. So you find the level at which the literal is present. Now the trick, of course, is I told you what to do if you are thinking of one literal at a time. If you have a set of literals, what do you do? That's what we'll spend a few minutes now. Okay? So if you have a set of literals, the one idea, suppose I wanted to say, what is the cost of on AB and on BA? Let's say. right? So I can do several things. Okay, one idea is to say, let me get the cost of RNAB, estimate for RNAB, estimate for RNBA, add them up, right? That would be essentially assuming independence of goals. Remember, when you have two goals and you have a plan of length L1 for goal 1, length L2 for goal 2, if the goal 1 and goal 2 are independent, there will be a plan of length L1 plus L2 for goals G1, G2. Right? So by adding them up, you are assuming independence. Okay, that's one idea. The other idea would be to say, don't act as if each of the literals are independent. Just look for the first level where the entire set is present. The entire set is present. And just take that level as the length required. Okay, so in one case I would have said RNAB is present in, so this is level 1, this is level 2, RNAB is present in level 2, and RNBA is present in level 2. So the cost of RNAB and RNBA together is 4. Okay, but even as I'm saying this, you're probably scratching your head saying, how can you actually get RNAB and RNBA together? But that's fine. In fact, RNAB and RNBA together would be infinitely long plan, because it's actually impossible. But 4 is certainly an lower bound than infinity. That's all we care for admissibility point of view. Okay, and more interestingly, suppose I said RNAB and so anyway, so in this particular case, RNAB is 2 and RNBA is 2, 2 plus 2, 4 is what you would have said if you went with individual literals. Okay, if you took the set as the first level at which the entire set is present, that's a set level heuristic. Right? Then you just look for the first set where both are present. It turns out this is the first level where both of them are present. Right? And then that's the length is 2. So you just say 2 is the underestimate. 2 is the heuristic. Now clearly notice that in this particular case at least, the independence assumption gave you a bigger estimate than the set level heuristic. From the point of view of cutting down the search, you want your heuristics to be larger numbers. Remember that? I mean, in fact, the best way to cut down the heuristic, cut down the search is to assume the heuristic estimate is infinity. Because then you won't do any search. Right? Okay. So, so independence will give you a bigger number. Okay. Set level will give you a smaller number, but it is actually admissible. Set level will give you a smaller number, but it's actually admissible. But oftentimes it may be too small. Okay, so that's what I'm going to, so to estimate the reachability of sets of literals, I have two ideas here. One is independence, make independence assumption. So the H sum, we call it, in fact you can also call it H ind or independence heuristic. H independent heuristic of PQR would be H of P plus H of Q plus H of R. And because it's making assumptions, independence assumption. And set level, basically if you define the set of cost of a set of literals in terms of the level where they appear together, then H level PQR is the index of the first level of the planning graph where P, Q and R appear together. So that way for us the number will be just 2 for RNAB and RNBA. Right? Now the interesting thing is this is all well and good, but remember if you remember actually from last time, we got into this idea of planning graph by saying, after all, heuristics come from relaxing the model. And our first idea was just relax the model by removing all the deletes and then solve the problem. If you solve the problem, you would have actually got a full plan for its, supporting the set of literals. These are not actually telling you what the plan is. They're just telling you essentially, this would be the this would be the estimate. Okay, so we'll get to this last idea called relaxed plan heuristic, which actually goes back to the first idea we had, which is relax the domain, solve the problem. That's the relaxed plan heuristic. Except now we will get the relaxed plan from the planning graph rather than actually doing progression regression. It will work, progression regression will still work, it's just that it's cheaper because the planning graph is sitting there already. Okay? Right? Okay, so before I go forward, I already said H level is definitely admissible. Right? How about H independence? Is that admissible? There is no always admissible. It's like, you know, so if it's not admissible in one case, then it's not admissible. Okay? So H independence is not admissible because you're making an assumption. You're making an assumption of, remember the only independence, positive interactions, negative interactions. Unbeknownst to you, the goals, the set of literals you're trying to estimate, right? They may actually be truly independent, in which case independence heuristic would be fine. Okay? They may be positively interacting, in which case independence heuristic would be overestimating. They may be negatively interacting, in which case independence heuristic would be underestimating. That would be fine. Yes, sir.
Do relaxed plans always amount to removing preconditions on actions, or are there other?
No, basically they're just assuming, we'll see in a minute, basically they're just assuming that two actions cannot interact because they don't have delete. So, you know, both of, basically, if one action is saying, you know, so like in the add delete list idea, basically you just remove the delete list. So actions only accrete. As you do actions, more and more things become true. Once made true, something doesn't become false during planning. That makes life much simpler. I told you this, right? In fact, in the database literature, you have this idea of query planning. Query planning has no negative interactions. So once something is made true, it will just be true. And that kind of a planning is easier than once something is made true, if you do some more actions, it can actually become false.
So you're actually removing constraints on the effects of action.
Exactly, you're just removing the deletes. Okay? Okay, so independence is, of course, not admissible because in the case of positive interactions, it will be underestimating. I mean, it will be overestimating. And since that case exists, it's not admissible. Again, there's a nice connection between the whole A-star search literature, A-star search discussion, and what we're doing here. Because we're actually bringing that back to bear on a different problem. Okay. Now, set level, is it admissible or not? Again, in set level's case too, unbeknownst to us, the set of goals may be independent, may be positively interacting, may be negatively interacting, or a combination thereof. Now, it turns out set level will always underestimate, irrespective of what is happening. In fact, the problem with set level is that it might be hugely underestimating. Not so much that it's underestimating, but it's hugely underestimating. And you know that you can always get admissibility badge by saying h equal to 0. And that's a useless heuristic. Set level can be somewhat too sort of uninformed among the admissibility systems. Okay? But it's not going to be inadmissible. Okay? So then the question, of course, is relaxed plan. Now, relaxed plan essentially says, so the place where set level heuristic becomes bad is exactly when there are positive interactions. There are positive interactions and you're missing the positive interactions. Okay? No, sorry. Where set level becomes bad is essentially if two things wind up becoming true by a certain level, it's assuming that somehow the same actions made them both true. But sometimes you might need one action to make this true, another action to make this true, and so total you use two actions, not one. The level just assumes that both actions are done at the same time, it's not counting the actions separately. So to put that in perspective, I'll show you two nice examples that you will remember. Okay. Here again, so neither H level or HSEM are actually particularly good. You know, and here are two examples that show it. So for example, consider a situation you are trying to compute estimate the cost of the set of literals P1 to P100. Suppose the situation was such that P1 is given by P1, P2 is given by P2, etc. P100 is given by P100. Right? Okay, in this particular case, the cost of actually achieving P1 to P100 is 100 because you need 100 actions. If you just went by level, level will say level 1. because you can do all of them in one level. So it will say 1. 1 is much less than 100. It's a very bad underestimate. It's admissible, but it's kind of very inefficient. Okay, in this case, HSUM actually wins. Right, because HSUM would have said this is 1, this is 1, this is 1, so I add up all ones, I get 100. Actually wind up being right here. So in this case, HSUM wins, H level loses in terms of efficiency. Here is a same kind of a situation, except it turns out that there's a single action B star which actually gives P1 to P100. Remember, anything can happen, because this is, all we are assuming is there is an action model, and the action model can, depending on the domain, might be of this kind of actions or might be this kind of an action. A single action winds up giving everything that's useful. Okay, and when that happens, when B star will give P1 to P100, this time set level is actually correct. Whereas independent would be very bad. Because independent will say the cost is 100 when the cost is actually 1. So it overestimates hugely as against underestimate. This one is, here H level is underestimating hugely. Here H sum or H independence is overestimating hugely. Okay. Now, if you look at this, you could say, why couldn't I have just somehow, I have this structure, why couldn't I have actually figured out how to make P1 to P100 true? Here is a simple idea. Okay, I need P1 to be true here, right? Okay, so find somebody who's giving P1 and say that you are in the plan now. Okay, so now P1 is being given by P1, you are in the plan. P2 is given by P2, you are in the plan. P3 is being given by P3, you are in the plan. Now the plan has 100 actions. You just add up the length of the plan. You take the length of the plan, that would be correct. That would work here too, because P1 is given by B star, so you are in the plan. P2 is also being given by B star, so you still are in the plan. By the end, the plan is just B star. So this is like a roundabout way of arguing that if you actually think in terms of plans, this business of H sum versus H level would go away. Okay, so what I need to actually do is sort of find, given the literals, I need to find a way of supporting them by actions. And when I support them by actions at this level, then I have to support the preconditions of those actions in the next level, and the preconditions of those actions in the next level. And when you do this, it's basically a plan. The interesting thing is you will never have to backtrack, because the way the planning graph is, you can always throw in actions and not worry that they can't be done together, because you're ignoring negative interactions. Do you see what I'm saying? Okay, so that's basically the idea of relaxed plan, and that's how it looks. So this picture basically is just a smaller version of this picture. Okay, now in this picture, all I'm trying to do is I'm trying to figure out the cost of